Good morning, or it's good afternoon. Good afternoon, everyone. Um, Welcome to this lesson. I think we, I think we are almost all there, so we can start. And sorry about this. My mouse is. Oh no, I don't know if I can get it. Yeah, it's okay. I think we have a quorum, so we can start. I think everybody is here. So we today we are going to look at uh, passband modulation. Last time we looked at the um, baseband modulation, but I thought before we go to passband, somebody asked me just to explain again FFT, particular aspects of FFT, and I thought maybe I can have maybe 10 minutes, look at it, uh, because I'm sure there are small things, but I did not write last time. Today I'm able to write. I couldn't I couldn't write, so I couldn't read, and I thought if you don't get past that, then you feel that the whole concept of FFT is a bit blurred. So I thought I just look at it for a few minutes. I hope you can see my presentation. I'm having digital carrier modulation. I want to change it to FFT. FFT. In fact, I also want to have on the screen DFT. Because there are some things 127, that is DFT. I think once I'm in PDF, whichever document I go to, you'll be able to see without uh, restarting the presentation. So one area where I thought probably there could have been some issues is, let's see through. I think everybody is okay up to here. I think nobody had a problem up to here. Here, of course, I told you to correct is W small n, W sub n. So I hope that is okay. But please remember when we say talks about complex conjugate symmetry and also periodicity, we are referring to this. Yeah, we are referring to Wn. Yeah, because Wn is given by this. So you can try it out yourself by actually checking the conjugate and also for, of course, this is periodic in 2 pi. Yeah, it's 2 pi periodic. It's a, this because these are cosine wave and uh, these are cosine wave and sine waves. Because what is this? It's simply cos minus j 2 pi over n. Sorry, not minus. J, I keep on putting j, remove j. Minus 2 pi over n plus j sine minus 2 pi over n. So once you understand that, now you can understand why um, me, some people here, why this is true. But actually what we are going to use is only this, the periodicity in periodicity in K and N. So it doesn't matter what the values of K and N are, since you're dealing with sinusoids, so you only be having multiples of 2 pi. Yeah. So that is not going to change. That's what we are saying is about this. Yeah. I think that I thought there could be confusion with that. I think here there's no confusion. Here is okay. So far, so good. I don't know where the problem was, but I decided maybe what I think. If you don't understand, you have a problem. This one, I think this one is simply what we are saying is e to the minus j to pi over n here. And we are saying if we square this, if you square this, because wn squared, if this is like multiplying by 2, which is like dividing the numerator by 2. No, the denominator, sorry. This is the denominator. Numerator is this one. Like dividing numerator by 2. That will be this. We have the same effect. Dividing the numerator by 2 or multiplying by 2. But now, by definition of this simply becomes W n over 2. This is W n, whatever is here. And what is here is n over 2. So that's what we are saying. If you square this, you simply get that. So I hope everybody is okay with that. I hope that was not the problem, but I'm only assuming it could have been a problem. Since I couldn't write, I couldn't explain that. Okay. Then the other place I thought I would explain, I hope nobody has a problem with this because it's just by definition. Here, I used instead of k plus n over 2, because even if you used k plus n over 2, it will still work. But I wanted to use to have xk going from 0 to 7. So I found that if you use that if you use for n over 2, k is equal to n over 2 to n minus 1, and you use k minus instead of plus, then it becomes, I mean, it opens very easily. You can now actually be able to see that x0 is equal to s10, w8 to 0, s2 0, yeah, and it goes up to x of 4 up to x of 7. But you see now from x of 4, you are going to use this formula. Yeah. So that is the formula from 0 to 3, and this is the formula which is the same thing, yeah, from 4 to 7, yeah, and that gives you that and that, yeah. So you're moving from 0 to 7. So this will be moving from 0 to 7. That is the power, because after all, the power of this is Wn to the power of k, yeah, because that's the formula, yeah. So I think nobody has a problem with that. If you have a problem with that, please raise your hand, yeah. So I hope everybody is okay with that. So in that case, that's what we get. We are saying this is n over 2 gives us that s1 of 0, s1 of 1, s1 of 2, s1 of 3. And this one s2, because you're saying this is the even and this is the odd. Yeah. So here we have picked the odd inputs. After all, that's how we are dividing our sequence. When we make it by 2, we are picking odd and even. So this is even and this is odd. And if you just go back to your formulas, we are going to find that x of 0 is simply s1 of 0 plus s2 of 0. But s2 of 0 is multiplied by wn to the k, which is this one. Since k is equal to 0, that is like multiplying with w8 to the 0. So this applies to this. Yeah. Always remember this applies to this. Yeah. Not to these ones. Even here and here, this apply to this because it is the S2 is S2 K, which is multiplied by W and K. So this applies to this. This applies the way I'm reading it. It could be a misunderstanding. So this applies to this. Yeah. So I hope again no one has a problem here. I hope it is clear. Yeah. So up to here is okay, everyone. Up to here is okay, everyone. Even the one who wrote to me.
For the last,
Yeah.
is the WN being multiplied to the S2 or the S1?
Yes, it is the S2 here, from here. It is the S2s which are being multiplied by W to the A, to WN to powers of K. Yeah?
Okay.
Is that okay?
Yes.
Okay. That's why we are saying that could be a problem because the way it's written here, you don't know whether it refers to this or to this. But just by definition, it is the S2s which are being multiplied by WN to the K. Yeah? So I agree here. If you just see it, it could be confusing. So from there, what we are doing for the four, for this we have just used A, B, C, D. So we have A is one of the n by 4 point DFT, and of course n by 4 is 2 point DFT. So it has only two inputs, x0 and x4. And okay, for this particular one is x0 and x1, but we have to pick the even. And remember, our even was 0, 2, 4, 6. Then we have to pick the even of this. So we are picking the even of this and the odd of this. Because now they are all even, but if you consider this to be the 0, 1, 2, so you are picking the even and the odd. If you consider this to be 0, 1, 2, 3, you are picking the even and the odd. Is that okay? That's why you're having 0, 4 and 2, 6. At this stage, you have that's the even and odd. So 0, 2, 4, 6 for this part, that was even. But here now you are dividing again to even and odd. So you can see why you have 0, 4 and 2, 6. Yeah. So we have just considered to be A, B, C, D. Some books you are going to find it calling it V1, V2, V3, V4, or just using another letter. Yeah. But I used A, B, C, D. So it will give us A0 and A1. For this particular one, this is A0 and A1. These are the Fourier transforms. Yeah. A0 and A1. We are going to find out how you get A0 and A1. B0 and B1. C0 and C1. D0 and D1. And what you want to get is the S0s. Remember, these are the S0, S10 to S1, S20 to S23. So I want to see how you get these and how to calculate here. Remember, we say S10 you are breaking now the S1s into two, each of them into two. So that is, so that becomes now, you can see that S10 is that, S11 is that, S12 is that, S13 is that. Then for these others, we are having now the S2. Again, the CS2 is being broken into this and S1 into this. So I think you can see why you can see why this is like this, because now S10 is equal to A0 plus B0 multiplied by this. Now, here I have used the WN, but you can also use W. The WN here can be 4 or 8. If you use 8, then of course you will be having 0, 4, 2, 6. You can use W4, then of course it is going to go from W0, W1, W2, W3. Yeah, and they are the same. They are the same if you come to this page here. W4 to the 0 is the same as W4 to, oh, not that one. W4 to the power of 2 is the same as W8 to the power of 4 is equal to this. Yeah. So you're going to find that by when, and also W4, what else? I think for all of them here, what I want to show you. Yeah. W4 to the 1 is the same as W8 to the power of 2. Yeah. And even W4 to the power of 2 is the same as W8 to the power of 4. W4 to the power of 3 is the same as W8 to the power of 6. So here, in the drawing, again, that could have been a confusion, moving from here to here, because now here I've used W4s. So I was thinking this could also be a source of confusion. Here, I said if you find it to in terms of WN, then of course it will be going from 0 to 4, 6. If you use WN over 2, which is 4, of course, to go from 0, 1, 2, 3. 0, 1, 2, 3. So I hope now we can see how you are getting this, and that's why you are doing this butterfly like that. So I hope again that is clear. The only thing I apologize for is because I used the W8 instead of W4, but it does not change anything. This is the same. These are the same. It's like using W4 0, 1, 2, 3. W4 0, 1, 2, 3. Okay, but I wanted to stick to the W8. Yeah, but actually, you look at the calculation, of course, we're talking about W4, but I put it in terms of W8. Yeah, yeah. So I think you can see how we get here, here. This one is straightforward. This one you don't even have to do. Here, here is just a matter of using the definition of DFT. So let's look at this. So I hope so far we are okay. Now I only want to show this one. Yeah. We go to DFT. So we are saying this is the definition of DFT. So if you have only two samples, what does it become? If this is x of k is equal to 0 to n minus 1, which is 0 to 1, x of n e to the minus 2 pi over 2, which is minus j pi, because this you have 2 pi over 2. So this will simply be 3 pi kn. So this means x of 0 is equal to x of 0 here, which is just x of 0 times this, when this is 0, which is simply x of 0, because when any of this is 0, yeah, and we are saying x of k is equal to 0, actually both are 0 because it goes from 0 to 1. So it starts with this summation. Oh, yeah, this summation. So this is simply x of 0 times 1 plus x of 1 times, you see, any of them being 0, we are dealing with n. Here we dealt with n. Remember, k is still 0 here because of here. So here n is equal to 0, and here n is equal to 1. So either way, this will just be times 1. Yeah, because one of them is 0. Now, x of 1 is equal to x of 1, because we are dealing with the oh, this is x of 0, of course. No, this is still x of 0, because n is 0 here. Then, and this is e to the minus, well, here n is equal to 0. So this is still 1, because you are starting with n is equal to 0 and n is equal to 1. So because of n is equal to 0, this of course is just 1. Plus, now here things will change. We go to x of 1 into, now let's think about this, e to the minus j pi. They are both equal to 1, so it is simply e to the minus j pi times 1 times 1. So this is equal to cos minus pi plus j sine minus pi. Yeah, and this is simply minus 1. Yeah, I think it's minus 1, is what we are saying. That this starts at 90, cos starts there. I think it becomes 0 at, is it at 90 or is it at 180? Oh, yes, but it becomes minus 1 at pi. Yeah, this pi by 2, this pi by 2 is an even function, so this becomes minus pi. So I mean, this is also minus pi, this is minus pi, so which is 1, which is minus 1, sorry. So cos minus pi is 1. That's the same as cos plus pi. So this becomes times minus 1. That is why, is that clear to everybody? So this simply becomes x0 plus x1 x1, and this is x0, I mean the capital X. These are small x's, sorry. This is x0 minus this x1. So I hope this is clear, because from here, that's where we are getting this. You can see, so it means x, look at them as just x1 and x2. So it is this plus this, but this other one is this minus this, you are multiplying it by -1 because of this what we just got. So at this point, all of them are just like that. Whatever is here, you multiply. Whatever is here, you add the 2, and here you subtract them. So is that okay? Is that okay for everyone? I think that's okay for everyone. Yeah, that's just cosine and sines of pi. So now we have that. So this is our complete. So this is the first one. This is how we are getting. Now it is N2. So that's what the second stage. And now this is the last stage is straightforward. Yeah. Is that okay? So this explanation, I hope everybody has no problem with it, especially here. We are saying the first split is simply uh, whenever you split is, of course, I think we have seen it somewhere. It is just n/2 squared, because we have said for n, when you do the DFT of n, you have n squared multiplications. So if you have n/2, then it will be n/2 squared. And since there are two, remember there is S1 and S2, you multiply by 2. And for each of them, you do n/2 multiplication. Which multiplication are we talking about? Is this multiplication? You see, there are these complex multiplications to get this, but there is also this multiplication. So we are saying there is n, and there is n squared, and then there is n. Just multiplying these two. These are n. Yeah, multiplications. Yeah, that's why you are saying n squared plus n. But so this will be n squared, and there are 2, and this is n/2, because now we are talking about the n is n/2. So when you multiply by 2, of course, it simply becomes n. Yeah. Then here we do again n squared. Remember, this n is still here now. We are still dividing. So this n is still here. But for this, we are going to get another n, because it will be 2n/2. So it gives us another n. So of course, you end up having n squared over 4 divided by 2n. And it will go increasing like that. So we can, that's what we are saying, is when n is for large n, is simply, because this becomes now n plus n log 2n. So now this is a bigger term. So we can ignore this term. So we are saying for large n, this is approximately this. Yeah. It will be approximately this. So I think that, again, I'm assuming nobody has a problem. Um, Moses, are you okay with that? Are you good so far? Moses Gray.
Yes.
Oh, you're good, eh?
Yeah, I'm good.
Okay, very good, very good. Sherry, you are good?
Yes.
Very good, very good. Now, how we use this? Of course, now how we use this. When you have everything, now it is easy to see how we will use this. We use a very small, a very simple example where all the samples were 1, and if you start from here, of course, you can see that is 1 plus 1, and this is 1 minus 1, so it is 0. So it will always be, this will always be 2, this is 0. 2 is 0. The others you just multiply with this. We know w to the 4, w4 to the 0 is 1, w4 to the 1 is j, w4 to the power of 2 is -1. So you just multiply with them. And eventually what we are going to get is simply w8. Oh, I did not show you. Yeah, what you're going to get, the final output is this 8000000, which you'll get the same if you did with a two factor, and you'll get the same if you used the tabular method. Not the tabular method, sorry. If you use this, you have to use this. It will work out to this. Because here you can either use the two factor or just work out the DFT direct. The tabular method is not for this, it's for the convolution, discrete convolution. Sorry about that. So you either use this, and obviously now you can see for yourself, you don't want to use this. You don't want to use this 8.2 factor. You'd rather use this, because now with this one you don't even need to even the 4.2 factor. You don't even need to use the 8.2 factor. Yeah. Well, you can use, but you are going to find that when you do this, you are doing fewer multiplication. Yeah, because this is a bit simple because it is 1, 1, 1. Of course, if it wasn't 1, 1, 1, you'd have to deal with this complex W powers of Wn. Yeah. So I assume everybody is okay. Is there anybody who is not okay with FFT? Yeah, I repeated it because the person who communicated with me told me that it seems to have been a problem of very many people. So with that, we can do. Yes, Tony.
Are you able to do a numerical example? Just an example
without without 111.
Yeah, just an example on FFT.
On FFT, actually, that's what we have done. We did one here, but with all inputs as one. The other thing I should have remembered to mention, yeah, this is actually an example. It's only that I chose an easy example to avoid having to work with this. But it will not matter if you had, for example, 1010001. It will still give you this a solution. But of course, in some cases, you'll be multiplying. For example, you see, like here, right? Like here, you see. In our case, Wn, we are not using this. You see, luckily we are not using this. But yeah, we are not using this actually. So I don't think it will even be matter much. You just be using J's. Yeah, because you're not using to the 7 anywhere. You are using to the W8 to the to these other powers from 0 to 6. Yeah. Yeah. Oh no, x of 7 would have this. Oh, W8 to 7. Oh, it's just because it doesn't matter what this is. Actually, you're using it, but it doesn't matter since this is 0, it just gives you 0. Yeah. So if we had chosen something different, you would use this also. By the way, you also use it. It's not correct that you're not using it. It's just that because of the zeros, it doesn't matter. So what you're multiplying with. Yeah. So that is the example we have done. Yes, George.
I have a question on if you are given a signal, say x of n,
Yeah.
which has 4 samples,
Yes.
and the impulse h of n has 2 samples,
Yes.
the convoluted signal's length should be 4 plus 2 minus 1, which is 5 samples.
Yes.
Can you use 4DFT to do the convolution?
No. You'd have to use you'd have to use 5 DFT. You see, it's just that DFT works very easily. Uh, well, for this DFT, to use FFT, then you need to do even numbers of samples. Yeah, for DFT, for to use FFT, because this is radix 2. But if you are going to use DFT matrices, then you'd have to work out what is a 5-point DFT. Does it make sense? Because the
Yes.
DFT does not have to be even. The DFT matrix, you can have 5-point DFT. Of course, you have a lot of very complex terms. Yeah, you can use that. But when it comes to FFT, you have samples which are even. Yeah, that's why we call it radix 2. It is in base 2. Is that okay?
Yes.
Okay. So let's know the two. There is using DFT and there is using DFT matrices, 4-point DFT, 8-point DFT. It can also be a non-number DFT. Yeah, it will still work, but it will be different. Normally, you find um, you use even point DFT matrices. So, for example, if you are doing that to use yeah, it will be a bit difficult to use the method where you're using um, circular convolution, because I was imagining you can use 8-point DFT so that you by the way it will give you the correct answer still, but still cut off at 5 samples. Are you Yeah, I'm thinking you can do it actually. Maybe you can try it with some actual examples. Like maybe you're given 101 and 11. So you can, by the way, you can use 4 DFT. No, you can't use 4-point DFT because it will give you only 4 samples. But you can use 8-point DFT. Yeah, by simply padding this with 5 zeros and the padding this with that. Of course, what you're going to end up with is a lot of zeros. So you can cut off at 5 samples, and then. Um, but of course, what is happening is you're only having this, but now you're having to do a lot of multiply all these bigger numbers. N is big, so you have more multiplications. Yeah, but this will still give you the correct answer. So you just uh, cut off at 5 samples, but you can't use 4 DFT. Yeah. So if that is okay, we still have 20 minutes. I think we can start off with yes, Samuel.
Yes, I had a more of a request.
Yeah.
So we've been doing an online lab in telecoms, but you realize the lab is designed in such a way some of the concepts we are required to simulate or design, let's say the filters, we
Yeah.
haven't yet covered in class. So I had a request, maybe if we could have 30 minutes of you helping us so that we can kind of have a direction towards what's expected of us in that telecoms lab.
Oh, the second lab you are doing digital filters.
Yes, and there are some concepts of the transform, there are
Yeah.
some concepts of uh, IIR, and you realize these are concepts we haven't yet covered in our syllabus.
Wow. Yeah, that is actually then we should have started even. eh, I, somehow I was informed that you are doing the filters lab in the second semester, or you're doing them now. Okay.
Sorry, I haven't quite got what you said.
Yes. No. I think the last time I talked to somebody in the lab. I don't know. Maybe I did not I did not get it right because I wanted to go to the lab and find out what you are doing in your labs. But I was informed that filters come in second semester. Digital filters come in second semester lab. That's what you'll be doing next semester, semester two. Now you're telling me you are actually doing them now, as we are doing, because that knowledge would have been very good because even we would have organized our uh, I mean, the sequence that we start with DFT and no, not with DFT. We start with the Z transform, and then we go to the how you use the Z transforms to do your filters. So we are using FIR filters or both IFR and IIR.
I have the PDF. I'll share it with you, but we're
Mm.
required to design finite impulse response, digital
Yeah,
filters, infinite impulse response, and then there are we are required to do it in MATLAB, and also there are Butterworth filter, Chebyshev.
yeah, which will be IIR. Eh?
Yeah, there's some kind of concepts which we haven't quite covered. So doing the lab has been a bit challenging. I'll share the PDF
Yeah,
with you.
kind of share. I think that's the issue we have when the lab is actually handled differently from the coursework, and I think I have not been having what you are doing in the lab. I've tried to find out because I think the lab handles so many subjects. So I think just send me that, and I think I also need to get in touch with the either lab technician or the person who is teaching the labs. Yeah, so sorry for that. But the next class, which is tomorrow, maybe tomorrow afternoon, we will start with the DFT. No, not DFT, sorry, with the Z transform, and of course, we'll go to the filter design, uh, FIR, maybe including IIR. We may need at least 3 double lessons. Yeah, but I'm sure even probably even with the first lesson, you could be having enough concepts to be able to do your lab. Yeah, but thank you very much for raising that. Yeah,
Yes, thank you.
yeah. because I always believed that is done in the second semester, the lab for FIR. So now I know even how to organize it. And somehow it has not been raised in the past years. But thank you very much for raising that. Because usually the order should be that. Okay, there are some cases whereby you do the lab and then do the coursework, but sometimes it's better to do not the coursework, do the theory. But sometimes I think the best is when you do the theory first, then do the lab. Yeah. And I think that's how it's been happening. You have been doing the theory first, the labs first, then you do the theory. Because you've always covered filters towards the end. Yeah. Yeah. But let's start looking at this topic which we had prepared, this DC modulation. We get out of our way. So once we start with the Z transform, we will go to difference equations and then to filters. So today we are going to look at the few remaining. We have 10 minutes, but we can start with digital passband modulation, which we also call it digital carrier modulation. We are using the carrier. From the test I gave you, and I think also the discussion we had on the first lesson, looks like, although it's in your syllabus, it's something you have already covered to some extent. So we just move through it very, very fast. We have already, of course, transmission systems can either be using baseband or passband. Baseband means no carrier. Passband means you're using a carrier. And we use a lot of passband, especially in wireless systems. In wired, we mainly use baseband, but in passband for wireless systems, we use passband. And there are three, I think this we are aware why you modulate. One is, of course, efficient transmission of the message signal for obvious reasons. Since you are transmitting wirelessly, the antenna comes in, and the size of the antenna is related directly to the wavelength. So one of the reasons why we want to go to a high frequency is to make it possible to work with the small, or rather reasonable size antennas. Yeah, because you're dealing with baseband, it also means the antenna will be too big. If you try to transmit in baseband and get reasonable gain, then it means you would have a problem of the size of the antenna. So that's one of the reasons. Efficient transmission. One of these, of course, is directly the size of the antennas. So you keep on going to higher frequencies so that your wavelength is low, is short, and therefore you can be able to have small antennas. The other one, of course, you want to enable multiplexing. I think you have come across that even in analog multiplexing. In analog modulation. So if you are dealing with, let's say, voice, and you mean voices together, you can't carry them at baseband together, they will interfere with each other, but you can modulate each of that voice with a different carrier and then transmit them together. Yeah, and you'll be able to demodulate them and recover your original signals. Yeah. So those are the main reasons. Now there are two. I'm moving very fast intentionally, but if of course you have issues, just raise your hand. My assumption will not be correct. So amplitude. So there are three types of digital color modulation. One is ASK, amplitude shift keying, phase shift keying, frequency shift keying. Of course, we use the keying because we are talking about zeros and ones. So at one point we are kind of going on and off. That's why we talk about keying. And of course, we have M array. Anything else other than binary, we call it M array. Yeah. Modulation schemes. That is, you're having multi-level signaling. Remember, when you have got binary, you have only two signals. So when you talk about multi-level, you are talking about you have many signals. Yeah, you have many symbols. The signals is what signal or symbol is what carries your information, your data, your zeros and one. So the binary, you have only two levels. In M array, M you have two to the M levels. Yeah. So if you are carrying 2 bits, you have 4 levels. You are carrying 3 bits. What it means, for each signal, you transmit 3 bits. So every time you have one signal, you have 3 bits. If it is if you are using 8 levels, 2 to the 3. Yeah. And so on and so on. Detection. I thought we would talk about detection. There are two types of detection. There is a coherent and non-coherent. This is supposed to be non-coherent. No coherent is non-coherent. Coherent simply means you need to have knowledge of the carrier phase, carrier signal phase. Yeah. So you can see definitely if your message is in the phase, then you need to know carrier phase. Yeah. So non-coherent, of course, things like phase shift keying, you have to use coherent. You can't use non-coherent. After all, if the message is carried in the phase, then you need to know if that's from where. You need to know the carrier phase. Yeah. Non-coherent is where you don't need knowledge of the carrier phase. Of course, non-coherent is easy to implement, but of course, doesn't perform as well in terms of noise. Doesn't perform as well as coherent. And of course, there are some modulations you cannot use non-coherent. So coherent detection is used for phase shift keying, frequency shift keying, amplitude shift keying. For all of them, you can still use coherent. But non-coherent, you can use differential phase shift keying and frequency shift keying and amplitude shift keying. You can see phase shift keying cannot be used with non-coherent detection. It is simple, does not you don't need to have knowledge of your carrier. So I'm sure even from digital modulation, from analog modulation, you could have methods of generating the phase of the carrier at the receiver. Yeah, I think one of it is what do you call that loop? It's I've forgotten the name of that loop. Yeah. So there are various methods. We are not going to look at them. They are the same methods which are used in the analog modulation. Yeah, and they are complex. That's why if you can avoid, if you have a chance of using a coherent, you use non-coherent because reproducing that phase from the received signal is tricky. Sorry for that. Yeah, so I think we will proceed from there tomorrow morning, and then we just finish this, and then we start, of course, with the Z transform. So, is there any question? Yeah, so tomorrow we are going to have lesson in the morning at 8, and then we are going to have the evening one at from 3:30. So for now, just post your registration on the uh, as text on the chat, and then we meet tomorrow. Very much.